Hello friends, welcome to my channel. This is Isro question paper from 2006 to 2016 vibration part 1. Question is, a mass m attached to a light spring oscillates with a period of 2 seconds. If the mass is increased by 2 kg, the period increases by 1 second. The value of m is how much? M is the mass. Initially, mass is m and time period is 2 seconds. Mass is increased by 2 kg, so final mass is m plus 2 and time period, this is m1 and m2. Time period increases by 1 second, so 2 plus 1, 3 seconds. Here we will use omega n, natural frequency is k by m root over, stiffness by mass root over. So we know omega n is 2 pi fn. So frequency fn equal to omega n by 2 pi. It's 1 by 2 pi root over k by m. So time period also we know is 1 by fn. It's 2 pi by omega n. So it will come 2 pi into m by k. T is proportional to m by k root over. This one we will use. Here T1 by root over of m1 by k equal to T2 by m2 by k. Stiffness is same both cases. So T1 is 2 seconds, m1 we know it's m equal to T2 is 3 seconds by m2, m plus 2 increases by 2 kg. So squaring 4 into m plus 2 equal to 3 into m. 3 square is 9. 9 into m. So 4m plus 8, that's it, right side 9m. If we will m equal to 8 by 9 minus 4m, it's 5. So 8 by 5, 1.30 by 5, 1.6 kg. Mass is 1.6 kg. B is our answer. A cantilever beam of negligible weight is carrying a mass capital M at its free end and is also resting on an elastic support of stiffness K1 as shown in the figure below. If K2 represents the bending stiffness of the beam, the natural frequency in radian per second of the system is how much? Omega n we have to calculate. It's k equivalent by m root over. So this we can represent like this. This beam also we can write it as a spring. Two springs parallel case. This is K2, K1, mass is m, capital M. So for parallel case, K equivalent equal to K1 plus K2. And for series case, series springs, it's K1 into K2 by K1 plus K2. This one we are not using here. We are using only parallel case. So omega n we have to calculate. K equivalent is, for parallel case, it's K1 plus K2 by capital M root over. This is in radian per second. From option C is our answer. K1 plus K2 divided by capital M whole root over. Which of the following relationships between the force F on a particle and the particle's position x implies a simple harmonic oscillation? This is a spring mass system. Initially, spring is having this much length. After that, one mass is attached. Mass is m. Because of mass, here in this direction mgw force will act. It will go up to del L, or x distance it will move. This is equilibrium position. This is 1 and 2. 2 is our equilibrium position. W is force or weight. W we can write as force F. So at 2, the equilibrium equation is, here again I will draw, one side force F and one side spring force K into X. So we can write this equation as F equal to minus Kx. Direction is opposite, so minus. So F equal to m into acceleration plus Kx equal to 0. This is simple harmonic equation. So x is displacement, first derivative x dot is velocity, x double dot is second derivative, it's acceleration. Mass into x double dot plus kx equal to 0. X double dot plus k by m into x is 0. And we know omega n natural frequency is root over of k by m. From here we will get that. This is SHM equation. This is also important. But in our question, here x square, b it's x square, so b not possible. Here it's positive 10x, so it is also not possible. D case x square, so it's also not possible. Only a is possible. And in case here k is 7. So a is our answer. Simple harmonic motion is very important for Isro. So many times asked. Next, a mass of 10 kg is held between two springs as shown in figure. Natural frequency of vibration of the system in cycles per second. This is omega n in radian per second, natural frequency, and omega n by 2 pi in cycles per second or hertz. Here this is the case of parallel connection. So K equivalent is K1 plus K2. Stiffness, equivalent stiffness is stiffness of both sides. You add this one, 20 kilonewton plus 20 kilonewton, it's 40 kilonewton per meter, and our mass is 100 kg. So we have to calculate natural frequency in cycles per second. So you have to check in which dimension they asked. Its unit is cycles per second. So we have to calculate Fn. Fn is 1 by 2 pi K equivalent by M. K equivalent by M is our omega n in radian per second. So it's in hertz. 1 by 2 pi K equivalent is 40 into 10 to the power 3 Newton per meter divided by mass is 100. So it's 10. 400 root over is 20 by 2 pi hertz or cycles per second. So it will come 10 by pi hertz or cycles per second Fn. This is our answer. From option A is our answer. Whirling speed of a shaft coincides with the natural frequency of its whirling speed. In this figure, shaft is rotating and this is our transverse vibration. It vibrates due to its weight W, supported by two bearings. Here one bearing, here one more bearing. It's transverse vibration. Whirling speed of shaft coincides with the natural frequency of its transverse vibration. Next, with symbols having usual meanings, the single degree of freedom system mx dot plus cx mx dot double dot plus cx dot plus kx equal to f sin omega t represents what? We already discussed. X is displacement, x double dot is velocity, x single dot, and x double dot is acceleration, and m is mass, c is damping coefficient, K is stiffness, and F is force applied. So force applied, so it's not free vibration. Free vibration without damping. C is here, so this is also not possible. Then D, forced vibration without damping. C is there, so it's damping. So finally C is our answer. Forced vibration with damping. For forced vibration F is present, so forced vibration, and C is present, so it's damping condition. In the two-rotor system shown in figure, I1 is less than I2. A node of vibration is situated where? Node of vibration. This is also here. Our formula is I1 into L1 equal to I2 into L2. Distance from node. So here given I1 is less than I2. I1 by I2 equal to L2 by L1. So I1 by I2 is less than 1. So L2 by L1 is less than 1. So L1 is greater than L2. So this is L1 and this is L2. Or L2 is less than L1. So from option between I1 and I2 but near to I1. Near to I1 means L1 is less than L2. So A is not possible. Between I1 and I2 but near to I2. In this case I1 and In this case, L1 is greater than L2. So this is possible. B is our answer. Exactly middle also not possible. Near to I1 means L2 is greater than L1. This is also not possible. Outside also not possible. B is our answer. The acceleration of simple harmonic motion of a pendulum is proportional to SHM is very important. So first displacement is A sin omega t, velocity is A omega cos omega t, first derivative, and second derivative is acceleration A omega square sin omega t. Here omega square into A sin omega t is displacement, so x double dot is minus omega square into x is our displacement. So x double dot acceleration is proportional to displacement or x. So from here D is our answer. Speed of particle executing simple harmonic motion with amplitude alpha is half of amplitude is a half of the maximum speed. At that instant, displacement of particle is how much? We have to calculate. Amplitude given small a. We'll write SHM. Displacement is A sin omega t, single dot. Velocity is A omega cos omega t. Here in this case given amplitude is half of maximum speed. Maximum speed is x single dot maximum is A into omega. In this case, which amplitude is half of the maximum speed. So our x is maximum speed half. We'll write this one. This is x dot. And from 1 and 2 we got A omega by 2 equal to A omega cos omega t. So cos omega t equal to half. So it's cos 60 degree or pi by 3. Omega t is pi by 3. At this instant, we have to calculate the displacement. Displacement is x. So omega t value we will put in x equation. A into sin omega t is pi by 3. So sin 60 degree is root 3 by 2. It's root 3 by 2a. This is our answer. At that instant, displacement of the particle is root 3 by 2a. Here it's small a, so root 3 by 2 small a. B is our answer. A block whose mass is 650 gram is fastened to a spring of spring constant K equal to 65 Newton per meter, whose other end is fixed. The block is pulled a distance x equal to 11 cm from its equilibrium position at x equal to 0 on a smooth surface and released from rest at t equal to 0. The maximum speed of the oscillation of the block is how much? Here if we draw this diagram according to data, we will get this type of figure. Here this is mass, spring stiffness given 65 Newton per meter, mass is m is 650 gram or 0.650 kg. It's displaced to this distance, x equal to 11 cm from equilibrium position, x equal to 0, and then release from rest. From t equal to 0, it's release. We have to calculate the maximum speed of oscillation. This type of question I already discussed in engineering mechanics videos. You can check in my playlist. The same work energy principle also you can use here. At position 1, potential energy, kinetic energy plus spring energy plus work done equal to potential energy, kinetic energy plus spring energy plus frictional resistance into distance at position 2. Total energy at 1 equal to at 2. So mgh at position 1, potential energy. Here potential energy same, and at initially t equal to 0, kinetic energy also 0, spring energy given, no force, no resisting force. In second case, at maximum speed, spring energy also 0. So only at position 1, spring potential energy equal to half mv square at maximum speed. Position 2, half cancel, k is 65 into x is 11 cm, so it's in meter, 0.11 square in, it's 650 by 10 to power 3 in kg. V we have to calculate v square. So 10 100 0.11 10 into 0.11 square is v square. So v equal to 10 into 0.11, so 1.1, v equal to 1.1 meter per second. From option D is our answer. Thank you friends for watching my video. Thank you.